Hi everyone. Today I wanted to provide a continuation on support vector machine from our previous machine learning tutorial. So what we discussed in the previous video was the concept of SVM. What is its main objective? What type of algorithm is it? The different terminologies associated with it, and how to apply the model on your data, as well as discussing briefly about the input parameters that it uses when attempting to do such classification. Previously on that video, we attempted to separate our two classes of data, and in that situation, we actually had our data linearly separable. So it means that we chose a linear kernel for that specific situation, because our data, when we plotted our points on the axes, we found that it was easily separated by a linear line. So in that case, we chose a linear kernel. But today, it's a bit different in the aspect that we are dealing with non-linearly separable data, as we will see in the next slide. So here we have two classes, the red and the blue class. But the question here is, can we easily and visually assign a line or separate these two classes using a hyperplane easily? And the answer here is no. However, SVM can actually tackle this challenge in a more different way. And this is where we are going to explain what the kernel trick is. I'm going to provide a really simple and clear explanation of what the kernel attempts to do. So first of all, you need to know that when the most famous kernel when dealing with non-linearly separable data is the Gaussian RBF kernel. And this is the most widely used kernel when attempting to deal with points scattered like that. And we will explain what an overall concept of a kernel is. So first of all, what the kernel here tries to do, or what many people explain in their blogs and tutorials, what it tries to do, or what the kernel trick is that we here have our input space. We have a two-dimensional space. So what it attempts to do is that it tries to separate between our two classes in this input space, in our two-dimensional space, without actually doing or exhilarating more effort to visit the 3 or 4 dimensional spaces or more in order to provide or allow a hyperplane or see how the hyperplane is going to exactly classify our classes or classify the data points. So in that way, it attempts to reduce the processing time in doing so. So instead of projecting each and every single point, let's say on a more or in a n-dimensional space, it does this classification on the two-dimensional space that we're currently standing on. So this is basically or intuitively what the kernel trick is. So again, it just starts to do this classification while being satisfied in the dimensional space that it's currently standing on. So it doesn't actually project each and every single point on an n-dimensional space and puts a hyperplane to classify between the two classes that we have here, the red and the blue. It actually remains in the two-dimensional space, for example, and it does its classification as if it were exactly in the n-dimensional space or in a higher dimensional space. So this is intuitively what people try to explain as the kernel trick. Okay, so what its advantages are is that, as I said, it reduces processing time, processing power, and it just makes the algorithm more simple in terms of computation. Here, I just wanted to illustrate how this can be done mathematically. I provided the most simple example that I could find, and just bear with me here. So we have, let's say this is x of I, this is a point that is in our two-dimensional space. And this point has its x and its y, so these basically are the coordinates. So mainly this is how this point is represented in a two-dimensional space on an x and on a y axis. So the standard way of projecting this point onto an n-dimensional space, and in our case it's a four-dimensional space, what we do is that the first step is that we have to transform each point to how exactly is it going to be located on this four-dimensional space. So we have here on our example points x of I and x of j. X of I is 1 and 2, x of j has coordinates 3 and 5. This is a very simple example. So the first step is that what we do here is that we transformed this coordinate or this point into, so here we have 2 points, xi and x of j. So we transformed each two-dimensional coordinate into how exactly would it have or projected as coordinates on the four-dimensional space. So we squared the first value, squared the second value, xi of 1 times xi of 2, xi of 2 times xi of 1. So this is just math, but this is the way in order to transform a coordinate on a two-dimensional space to a n, or in our example on a four-dimensional space. So we did so for the 2 points that we here have, xi and xj. Then I want to know how exactly are these 2 points going to be projected from each other. So we provide the dot product, in which we say between the two vectors, 1 times 9 plus 2 times 15 plus 2 times 15 plus 4 times 25. So these 2 steps allow us, or allow mathematicians, to know exactly how we are going to project these 2 points on a four-dimensional space, and how they are going to be projected, actually these 2 points, how they're going to be projected from each other. So this is basically what we do in terms of math. But the main purpose here is not understanding the math. The main takeaway from this specific slide is that when we attempted to project on a higher dimensional space, we had to transform our coordinates in order to do so. When we transform the x of I and x of j to these new coordinates, they're actually the same, but a projection on a higher dimensional space. And this is the main thing that I want you to focus on, is that we had to transform, we had to project on a higher dimensional space. So this is the standard way in which we can do so. And here is where the kernel trick actually comes in. Because as you can see here, we tackled the same problem, or it's actually not a problem, the same challenge, but in a different way. We were able to project the 2 points from each other while being in the same dimensional space. So what we did is that we multiplied 1 times 3 plus 2 times 5 to the power of 2, which gave us the same value, which is 169. So here, the difference is that we projected on a higher dimensional space. However, in here, in that, when we use this or another function, which is going to be our kernel function illustration, we actually did so without projecting our points onto a higher dimensional space, because the main objective here was knowing how the 2 points are going to be projected from each other, what their distance was going to be from each other on a higher dimensional space. So we did so without actually transforming our points. So imagine that you have a training set of 10,000 or even more records, and you're going to transform each and every single point on a higher dimensional space. So it would take so much time and processing power in order to get this done. However, this is the purpose or the objective of the kernel trick from a really shallow and really simple example, is that we were able to get a function that provides me with the same value without actually going to a higher dimensional space in order to do so. So this is basically what the kernel trick intuition is, the main purpose of the kernel trick. Here in this slide, we're going to discuss our kernel for dealing with nonlinearly separable data. And the most famous and widely used kernel for dealing with nonlinearly separable data in SVM is the Gaussian RBF kernel. So this kernel attempts to do two things. It attempts to project our data points onto a higher dimensional space without actually visiting that n-dimensional space. And the second point is that it tries to balance or to achieve the optimization problem or the optimization step that we want, which is what we discussed in the previous video, is that we want to achieve the concept of the maximum margin, which is basically maximizing the distance between the support vectors and our hyperplane. The maximum, the better. But however, when the algorithm was introduced, this is basically the kernel. Okay, so it attempts to do those two things. It attempts to project and at the same time maintain or achieve our optimization challenge. So at the end, they reached this mathematical equation or this function without actually taking our points and projecting them to a higher space. And at the same time, separating our points, providing a hyperplane that does so, and achieving the optimization challenge that we have. So this is the Gaussian RBF kernel. This is the kernel that they introduced in order to solve our challenge here. And what we want to also discuss in this slide, what exactly does this mathematical equation attempt to do? It's very easy and very simple. In our case here, we have X and L. L here is considered to be our landmark. So let's assume we have the X and the Y axis. So our landmark that we chose is 0, 0. Okay, so this is the origin. And the X is any point that you can possibly choose on the X and the Y axis. Okay, so what here we do in the numerator of our power here is that we attempt to see the distance between the point that we've chosen and the landmark. And this equation attempts to do so using the Euclidean distance. And you can search for this this mathematical equation of what the Euclidean distance is calculated by. However, it attempts to get the distance between our point and the landmark using the Euclidean distance. But what you need to know without going into deeper mathematics is that this is the distance between our point and the landmark. Okay? And then in the denominator, we have here the gamma or the sigma. And here we're going to explain this value, and you're going to know its effect in upcoming slides. However, what you need to know about it this far is that it is responsible for saying whether this curve is going to be steep and high or whether it's going to be low. So it has a say in how exactly the curve or the bell-shaped curve of our kernel is going to be like. It has a say in introducing the boundaries of the kernel. Okay, so whenever you increase the bell-shaped curve, whenever you have a control in how your region or your kernel region is going, or the deciding region is going to be like. I also want to make it also clear is that this illustration is only for us because the kernel, as I said, it doesn't actually visit this three-dimensional space. This is just for us to visually know how it tackles this separating challenge that we have using the two-dimensional space that we're currently on, because here we're only using 2 points, the x and the landmark. Okay, so this is for us visually. However, it doesn't actually visit a three-dimensional space. Here the kernel is just staying on the two-dimensional space using the concept or the explanation that I have just provided minutes ago. So the key takeaway from this slide as well is that I wanted to focus more on the gamma or the sigma here and say that let's just go into a little bit math. Whenever this value, this sigma value is very high or has a very high value, what happens here is that the overall power value is going to be small. And whenever we have e to the power of something which is small, it's going to go upwards. So by increasing the value of the gamma or the sigma, here I have an overall small value. And e to the power of something negative, something small, it actually it will give us a value near to 1, going upwards. So it will provide a curvier, bell-shaped decision boundary or curve. However, when I have my sigma, or I have this value, okay, the gamma value is very of a smaller value, this power value is going to be a bit greater or a bit larger. So when I say e to the power of negative, a very large number, the value or the overall value of this equation or this function is going to be 0 point something or 0.00 something. So it's going to be at the lower position, or in that region, in the blue region. It's going to be downwards of the kernel or the curve that our kernel has decided upon. Okay, so the greater the gamma, it's going to provide a curvier or a steeper bell-shaped curve. But the lower the gamma, you're going to find the points lying in this blue region. And this is the key takeaway of knowing in future slides what the gamma here, how it tries to manipulate the decision boundary. Going on to the SVM parameters. So we have agreed that the kernel is going to be equal to RBF. The gamma, let's say we chose a small value for the gamma, and we chose the value of the C, which is the default value. It's going to be 1. The random state is just here in order to provide us with the same results. When you're attempting to apply or to fit your model on your training set, it just attempts to provide the same results. And then we're going to visualize what exactly the output is going to be using these parameters. And by the way, the random state, it's not necessarily crucial to be input. It's just when someone wants to obtain the same result as another one, or as another person who is attempting to fit your model on your training set. So this can be disregarded. Okay? So here, let's play around with gamma. So we have decided that the gamma, what it does is that it controls the decision boundary of the curve. So here we have a very small, we started by a very small value of, or for gamma. It's 0.01. So you can see here how the blue from the red points are classified. However, we have started to increase the value of gamma, also taking into consideration that the C value is constant. So our C is 1, okay? So our C is a constant value, but we're playing around a bit with the gamma. We've increased the value here of the gamma, and it's now equal to 1. So you can see here that the decision boundary has changed. It tried to change a bit of how the points are, or where the regions are going to be located while attempting to classify between these two classes. We've also increased it to 10, and then we've increased it to 100. So you can see this is a maximum value of the gamma. So you can see that the decision boundaries are relatively made for grabbing each and every single red point belonging to the red class. So this actually is on a two-dimensional space. But when attempting to visualize it on a three-dimensional space, this curve actually becomes more higher and it becomes more curvier. So this is basically the influence of increasing the value of the gamma, in which I have illustrated here on this function, or on its on the RBF kernel function. So returning back, so this is the maximum value of gamma, and you can see that it actually brings in the fear of overfitting our model on the training set. However, the aim is just knowing how this gamma, while increasing its value, it's going to provide or influence how it influences the decision boundary. Now let's play around with C, keeping into consideration that our gamma is of constant value. So we have a constant value of gamma, but we are keeping the C, or now we're changing the values of C. In the previous video, I explained what C is and the influence of increasing and decreasing its value. But let's now recall that C is more concerned with misclassification of the classes instead of providing a decision boundary. It just tries to provide a penalty if a point is misclassified. So here, this is the default value in which the red and the blue points are classified. When we attempt to increase its value, you can see here that it tries to also take the blue points on its side. So it's more concerned with misclassification, okay? And here you can see that decision boundary is the same, Okay, the decision boundary is not actually being influenced by changing the value of C. Instead, it's more concerned with misclassification of the points. And this is an incredibly large number of C. But you can see here the decision boundary is still the same. However, it's more concerned with misclassification of the points between the two classes. So manipulating the C does not influence the decision boundary. However, what it does is that it tries to prevent this misclassification of the data points, keeping the curve on the same boundaries as it is. So this is basically the difference between the gamma and the C. So the takeaway from this slide is that, gamma is more concerned with the decision boundary, which is the demonstration of the curve of the kernel. But C is just concerned with misclassification of the data points. So the question here is, how can I choose the optimal values of C and gamma? It's actually a trial and error scenario, in which here we played around with different values of gamma and different values of C. And we have decided from this heat map that the optimal value is this square, which has a value of gamma of 0.1 and a value of C of 1. So you can also, instead of plotting in a heat map, you can just calculate the score or the accuracy score of different inputs. So this is actually what the SVM does when it tries to approach data that is linearly non-separable. I've tried to simplify it as much as I can, so I hope you now get this whole logic and the whole purpose and what the kernel trick is actually based upon, and how they try to approach this problem without actually going into a higher dimensional space. So I hope this clears things out. So if you've understood this video clearly, please give a thumbs up and subscribe to my channel.